So I hope none of my experiments are examples for your worst case scenarios, but they may be.
Well,
I know.
Since you already know Latin, I doubt that will be the case.
So I want to talk a little bit about increasing precision in agronomic field trials using the Latin square design. This talk developed out of our frustration in the inability to get, how did you say it? The significant difference. I think we talked about. People in marketing will say, well, what's the significant difference? What's significant? And working with plant growth regulators, we were just pulling our hair out because there are so many things that impact it. Can you imagine working with a growth regulator that's a gas, ethylene, in these plots? And we're controlling ethylene with our treatments, but we're surrounded by border rows and control plots, and guess what they're doing? They're giving off ethylene, and it's drifting across, and it's screwing everything up. So significant difference. I mean, it was quite an experience. So let's see.
Did he stick in? You may have to use the keys if you
Okay, it's not active.
Oh, hang on a second. I need to switch it back to the.
that's right.
Switch it back to the.
Here we go. Wow,
It has two different modes.
how neat is that?
No.
I just want to advance, that's all.
Yeah, you may have to do it.
Okay.
You may have to do it this way.
I can do that.
Yeah, but this is the.
Okay, I'll just wave my hands, that's fine.
This is the.
Okay, great. So I sort of set the talk up so we've got an overview, and then I'm going to tell you what I'm going to tell you. Then I'll tell you it, and then I'll tell you what I told you. So this is where we're going, and I want to just give you a quick overview of what some of the slides we're going to see look at. Some information on research strategies and principles of design. A little bit on randomized complete block design, which is the holy grail of agronomists. Some discussion on the sources of variation and our frustration with dealing with plant growth regulators and trying to control those sources. And that's what led us to the Latin square design, which I'll focus on. And then I've got a couple slides on the relative efficiency of randomized complete block versus a Latin square design. Then I'll close with a case study of 30 trials done across the Midwest on a variety of crops, some university cooperators, some third-party cooperators, and I'll show you how the Latin square sorted out versus the randomized complete block. So as we develop a research strategy, the number of treatments is very broad in the lab and when we're doing basic research. So it's a huge scattergram. We're looking at lots of relationships, maybe some greenhouse work. And then the scope of inference moves up and the number of treatments narrow in the developmental research, small plot studies, and then the adaptive research on station studies. This is the area of the triangle where we're working with these small plots. And typically we're looking at treatments, dose responses, and then treatments by environmental responses. And then only at the top, as we discussed yesterday, is management a major factor where you integrate in a large farm or strip trials, environment treatment and management. So Edward, thank you so much for going over these terms. I think we're all on the same page, so I won't spend a lot of time on that. It's in the slide deck. So this is the paper that led us to conclude, hey, there's a problem in the way we as agronomists do our work. S et al. In let's see, I don't have the date on here, I guess. Looked at trials from 2001 to 2003 and looked at the kinds of designs that were used. And also, this has got some treatment and rep data. It's a real nice paper. I included this paper on the stick in your handout so you can look at it. There's a lot more to it than this table. But this table is what shocked us, that this is dogma in our industry, randomized complete block. One Latin square, and you can see the replicates typically are 4. And so we ask why? How does this happen? Why is this dogma? And maybe you have some insight to it, because we teach our graduate students and they teach their students, and it becomes so ingrained in our culture and nobody looks up. So the principles of experimental design have to incorporate, as you indicated, replication, randomization, sort of blocking, and those are the major elements of fundamentally sound experiments. It's this blocking parameter that causes us heartburn, because if it's not fine enough, it won't catch all the variance, and it won't eliminate the variance so you can see the signal to noise ratio. So a typical randomized complete block design might look like this. Blocks going this way, perpendicular to a gradient. And you can hypothesize what those gradients might be: fertility, water, slope, air drainage, whatever. And if you look at the linear additive model for randomized complete block design, you see that the dependent variable, y, I through j, is made up of an overall mean, the block effect to the I block, and the treatment effect to the jth treatment, and a residual error term. So we adopted the idea of randomized complete, we abandoned the idea of randomized complete block and adopted Latin square, and all of our protocols that went to 30 cooperators in the Midwest were designed for Latin square. But most of these cooperators were most comfortable with randomized complete block. Many were using ARM, and so ARM. So they liked that. It was easy for them to do. And in spite of the fact that we constructed the experimental design as a Latin square, they took the data and processed it through their analysis of variance in the ARM system. So we got data back, even though it was set up as a Latin square, analyzed as a randomized complete block. This is one of the data sets we got back. And the conclusion was, because of the high level of variance, there was no difference between these means. And we really scratched our head, because we knew we had active molecules, and this wasn't supported by what we saw in the lab in the greenhouse.
Richard, what are the error bars in this case? Are those standard errors? Or
Those are standard errors, yes. Mm-hmm.
They didn't take advantage of, the analysis didn't take advantage that it is in fact an analysis of variance, because they just used the individual treatment variance.
That's right. So how does this happen? How do we get something that looks like there's some mean separation, but there isn't? And so Kassler, and I recommend this paper too, it's good, came up with 4 ways that this might happen. A poorly designed experiment with insufficient power to detect the differences between treatment means. Poorly designed treatments that didn't reflect the initial hypothesis. And in that design, we always try to include not only a negative control, but a positive control. So in the weed science system, we have a real weedy plot. Then we have a hand-weeded plot. So you have a negative and a positive control. The hand-weeded plot's the one to match or beat. With plant growth regulators, we've got a mixture of plant growth regulators that work every time, and they're very consistent. That's the high bar. And if you can't beat that, go home. It's as simple as that. So a negative and a positive control are important. An improperly conducted experiment without proper oversight over treatment applications. And Ron, you talked about treatment applications on corn leaves, a surfactant, drift control, lots of components there. And of course, data collection. And the lack of a true difference between the treatment means, of course, wouldn't give you any separation. So if we look at the principles of blocking, the textbook explanation is a plot-to-plot variation within blocks is smaller than the block-to-block variation, so you should be able to see a good signal-to-noise ratio. That makes the assumption that you've got some prior knowledge of the site variation. How well do you know that site? What's the history of that site? How many rotations do you go back? The blocks have to be oriented perpendicular to the gradient. And the variation actually follows a gradient. Imagine that.
How do you deal with situations where there's more than one gradient? You just pick a different field?
I thought you'd never ask.
Oh, I'm sorry.
Yeah, we're going there. So this is a ground view of a 30-inch row-spaced corn. And you can see the plants from the ground looking out. They look pretty thick. And there's soil visible between them. If we look at the same plot from the air, it looks very different. So the aerial view of the same field taken on the same day, notice how you see mostly soil differences compared to plant differences. And so here we're seeing a difference in soil, whatever the characteristic is, but there are lots of sources of variation. Here are tile lines visible in a field. Can you imagine doing a randomized complete block on this? Which way's the gradient? What about equipment patterns? How long has this been farmed? And what's the favorite pattern going through that field? It's the same every year. And so you end up with a patchwork. I know when I mow my grass, I've got a part around a flower garden. It's got a little trench for my mower wheel. I go around it every time. Same here. How about anhydrous ammonia skips? Think that'll have an impact on our experiment? Absolutely. This is one of my favorites. Uneven distribution of crop residue. Remember when they stopped the combine and blew all that stuff out and they just left it there? There it is. So how do we deal with that? How do we deal with these gradients of variation, known and unknown? You can't just account for variance in one direction and make the assumption there's homogeneity in the other direction. You have to assume that your experimental design has gradients in both directions, and you better capture the variance associated with that gradient. And so we went to a Latin square design. It reduces experimental error by blocking on two perpendicular sources of variation. Essentially, you're simultaneously capturing the two sources of nuisance variation, and it allows you to tease them out from your signal. Each treatment appears only once in each row and each column. So if you notice, the columns only have one of the treatments, and the rows, it's a very prescribed pattern. And we actually give this to our collaborators. This is the way you put it out. The treatments equal the number of replications. So if you have 4 treatments, you have 4 reps. So you have a 4x4 square, a 5x5, a 6x6. We like the larger squares because it gives you more degrees of freedom. The small squares suffer from a degrees of freedom issue. So if we look at the linear additive model for a Latin square, we see that the block term now is split in 2. We have a row term and a column term. And so we can separate the error effects contributed from each one. So going back to the original data that we looked at, continuing to scratch our heads, we said, let's visualize this data. Let's chart it and see what it looks like. And so here it is, yield in bushels per acre by rows and by columns. You think there might be some variation there? It looked to us like when we do it by rows, there was sort of an increasing trend through the row pattern. And then when you plot the yield by columns, there's a decreasing trend. Something's going on. So this was data, remember, that was from a Latin square, but the collaborator did the ANOVA as a randomized complete block. And so I guess I don't want to spend too much time on this. Let's see if we can get, okay, good. So here the rows are as a block. Here the columns are as a block. And you can see there's no good mean separation in either one of these. But if we look at the rows and columns separately as a block, we do have mean separation. And we have, for field data, an alpha that is less than 10%. So it's something that we can use. And so if we look at the chart now, suddenly it becomes meaningful. Because we've removed the error, rather than lumping those error terms in this large block term, we've split it out into that variance contributed by rows and variance contributed by columns.
Why do you have different length error bars? They all should be the same. If you use a residual error term and you have equal replications,
Yes.
you would have, by definition, in an LS design, all the error bars should be the same length. They're not.
You're right. That's my bad on duplicating a slide and pulling it across. Yes, you're absolutely correct.
Question, do you find this, does the size of the actual plot design affect the quality of data with the Latin square? Like, in other words, do you see more value of this when you're going to larger field scale replicated plots than you do with small scale replicated plots? Because, and the reason I ask is that a lot of the contract researchers that I'm using, I'm very familiar with their very uniform, and we try to select those areas that we're trying to take the variability out.
Sure.
And I can see where this would be really useful on a larger replicated farm trial. I guess I'm not looking for some input.
Our experience is that it depends on the kind of treatment you're looking at. There's clearly an outside row effect. If you're going to extrapolate any of this yield data into bushels per acre, it becomes bogus very quick because you're multiplying a number by 1,000 to get the bushels per acre. So it becomes silly. If you're doing something that involves insects, you've got a lot of side effects coming in, so you need bigger blocks. With something that goes in furrow, not so much, or a seed treatment, not so much. So it really depends on the treatment. That's been our experience.
All right, thank you.
So a couple slides on mean separation. on relative efficiency of the two comparisons, I'm not real familiar with this, but we dug through the literature and looked at Kuhl's paper, and sure enough, if you compare with a randomized complete block design using rows as the block, there was an efficiency gain of 3.7 by adding the columns. Likewise, looking at the same data using the columns as blocks, when you add the rows, there was a gain of efficiency there as well. So we came up with a hypothesis, and the hypothesis was that soil heterogeneity is more prevalent and in two dimensions than we assumed that it was. And so we designed an experiment with the objective of evaluating the use of Latin square design to control soil heterogeneity and compare the relative efficiency versus a randomized complete block. And so these are the 30 studies that we looked at, the locations: 12 corn trials, 13 sorghum trials, 15 soybean trials, 18 physical locations in 10 states, and we had cooperators both at land-grant institutions and contract field cooperators. So it's a pretty nice distribution, crop-wise and location-wise. We discovered that the presence of gradients exhibited in the 30 Latin square trials conducted over the 18 locations in 10 states across the upper Midwest. Only 4 of the trials, 13, did not exhibit a significant gradient, indicating blocking is a sound practice to help control variation. So there was essentially no gradient here, one-way gradient here, two-way gradient there. Fourteen of the trials, or 47%, exhibited a two-way variation, and the precision was increased, the lower mean square, by using the Latin square design.
Can I ask you a question?
Sure.
Are you going to... One question I have is, how do you detect the gradients? So I mean, we can all imagine very simple gradients, and we say, okay, there's going to be this gradient, but when you're looking at a field or you're looking at an environment, how do you detect it? Are there standard methods? And that's one question. And then the other one is when we were looking at the Latin square design, we had 2 perpendicular gradients. What happens when they're not that neat? When the gradients intersect in a different way? Is it still valid and better to use a Latin square design versus, say, RCD?
So your questions are certainly related. The answer to the first question is, I have no idea. I don't even know what they are. I mean, is it nitrogen? Is it phosphorus? Is it nematodes? Is it sandy loam? Is it compaction? I have no idea. What's the history of that field? I don't know that either. So I don't know what they are, but what I do know is if you ignore them, they'll bite you. And they'll generate so much noise that you'll never see a difference. So I don't know what they are. I can't find out what they are, but I can control them by looking at the gradients. I don't think it makes any difference, and I don't think the gradients are that clean. I don't think the orientation makes any difference because your replications pick up the noise. And Edward, maybe you want to comment on that too.
Well, another way to approach the, let me wait for the, I know my voice carries, but may not carry to the mic back there. Another way to approach is to do blocking, but then employ some residual modeling. I mean, in the past, what people have done, they've done nearest neighbor analysis, which treats the residual variance as a fixed effect. But you can actually do this as a random effect and model the residual variance, and there are various models that do not assume linearity, and it would be I would love to get a hold of that data set and actually do that. And you can model it, and you can get quite a bit of gain in efficiency. that depending on location where your treatment is, you may actually have different residual variance terms now.
Excellent. So overall, the precision was increased 70% in 21 of the 30 trials by using the Latin square design. Of the, so we've got, of this 12 here, which were one-way gradients, 5 of those remaining one-way gradients from the randomized complete block design would have more precision if the blocking had been chosen in a different direction. So what you do if you're doing randomized complete block, you're leaving it to luck which way you block it. If you block it perpendicular to the existing gradient, you know what the gradient is, you're okay. But if you don't catch that or it's not identified, it bites you. So the interpretation and conclusion is that multiple gradients are prevalent. Most of them are unknown. And does it matter if we identify them? I don't know. I don't think so. But we do need to deal with them and capture the variance that they contribute. Blocking in a single direction will only increase precision if the variation is successfully captured with those blocks. If you guess wrong, the signal-to-noise ratio goes crazy. The Latin square increased precision in over 2/3 of the trials we evaluated. Efficiency is not sacrificed if there just happens to be a single gradient. So you don't lose anything by using this design, and you really protect yourself. These trials can be expensive. The number of treatments is restricted to an equal number of replicates, and the degrees of freedom can be an issue for the small squares. So we covered a lot. Research strategies and principles of design focus really in that center area of adaptive research, on-station studies. The fundamentally sound experiment incorporates replication, randomization, and I would propose that this blocking needs to be broken into 2 parts, variation in 2 dimensions rather than just 1. What are the sources of variation in the field? I shared with you a couple. I'm sure if we go round robin, we'd never run out of things to list in this group. The features of the Latin square we talked about. It's a square. The number of treatments equals the number of replicates. We've adopted a 6x6. It gives us a nice number of replicates. It's easy to manage. The efficiency is typically, relative efficiency is typically better with the Latin square than the randomized complete block. And we validated these concerns in 30 trials conducted in the Midwest on corn, soy, sorghum, and soy. I've shared with Ron and Dan 2 papers on my stick. One of them is the seminal paper by Van Ness looking at spatially balanced complete block designs for field experiments. That's the one that had the table in there that surveyed all the agronomy journals articles for 3 years and showed that 97% of them had randomized complete block. So it's, just this is the way my grandfather did it, this is the way my father did it, this is the way I'm doing it. Not a good idea. The information that I shared with you is published in a paper by Jones, Woodward, and Stoller, Increasing Precision in Agronomic Field Trials. I don't know whether there's enough raw data in there to play with, but I can certainly share that with you if you want to do it. And what's really exciting now is people are actually reading our paper, and I just did a quick citation search, and some of the folks you cited are actually citing this paper and getting on board with the idea that, hey, we need to control variance in 2 dimensions, and there's some merit to doing that. So maybe we'll see some disruptive technology in agronomy that's going to lead to better experimental design.